One overarching goal we had for the math activities were that they were rich mathematically, and they also serve the science. The timeline activity begins with asking participants or asking students to make a personal connection. The idea of this activity is it begins with the question, what is the oldest living thing that I've ever seen? So the oldest living organism that I've personally seen, which I'm definitely far surpassed, but is El Gran Biznaga. It's in the Botanical Garden in Oaxaca in Mexico, and it's estimated to be 1,000 years old.
I actually hugged a 600-year-old tree in New Hampshire.
Did everybody hear that?
Pointed out to me, and it was 600 years old, and I forget if it was a hemlock or a black hickory, but I wish it could talk to me and tell me all of its wisdom.
Quaking aspens are a living organism that are connected all underground, and their root structure is hundreds, tens of thousands of years old.
So the next step is to talk about the history of the Earth and just to throw out the number of how old is the Earth. So we're going to be thinking a little bit about that, and we're going to start with the ship that we're all on, which is the Earth. Spaceship Earth. How old is the Earth? Anybody know?
6,000 years.
6,000 years. That's one answer.
6 billion.
4.6 billion. And so 4.6 billion years came out. The Earth is 4.6 billion years old. And so the next thing I give them was a chart that looked at the different eras, the timing of them, like how long each one was and how many million and billion of years ago it was. And I just had them look at it. And the two questions that I had for them was, what do you notice? And what questions do you have? The one thing I really wanted them to notice is the idea that 90% of the history of the Earth happens in the tiny little line, the Precambrian period at the bottom of the thing.
What did you notice?
The scale is off. It really bothers me.
What do you mean the scale's off?
On the Cambrian.
Yeah.
Okay, so that little chunk.
Oh, it's the big, so it comprises the biggest amount of time.
Yeah.
The scale is important. So the activity to kind of explore that idea was to create a scale timeline of those 4.6 billion years. You are going to be working on, to scale, geologic timelines for the history of the Earth. They were broken up into groups. Each group was given a 5-meter long strip of paper and Post-its and markers and rulers. I threw out the suggestion that they might think about 1 billion years for each meter, and then it was just to let them work. And I gave them a sheet that had significant events in the history of the Earth that they had to place on that timeline. There's this understanding that's developing that the Earth has been around a lot longer than we thought it was.
Hi, our group created a scale timeline of the Earth's history. Each meter was equal to 1 billion years old. We originally started with the origin of the Earth, which was 4.6 billion years ago. As we progressed down through, we noted that 3.8 billion years ago was the oldest known rock. The oxygen-producing bacteria, the algae occurred 3.6 billion years ago.
One of the events is the appearance of Homo erectus, which is 2 million years ago. It's a very small scale, and then even Homo sapiens appeared 200,000 years ago.
So, evolution of hominids 2 million years ago. So we are like here.
So we can draw a person.
Yeah.
The question of how they were going to represent that on the scale was a way of making this proportional reasoning activity problematic, because they had to make decisions and choices, and groups did it differently.
We made our scale, using the guide that Mark said. So we used a meter for 1 billion years. And then we went in and marked each significant event using that same time scale. So what I was just saying to you, so 10 centimeters equals 100 million. So we only started marking 1 million at 500 million years ago. The rest of it is in billions. But so then this last 50 centimeters is the last 500 million years.
What I really like about this activity from the perspective of mathematics is the challenge of the scale. This is an incredibly rich activity. It takes a long time, but students can absolutely do it. They definitely need support. Ways that you might adjust it are choosing fewer events. But another way that you might adapt it, but also a way that you might continue and build off of an activity like the timeline activity, teachers can kind of separate that into layers. And so you study something about plants and like the evolution of plants, so let's put that on our timeline. Or same thing with animals, and kind of focus on these strands. There are really all of these different layers that you can look in that I think it would be really nice to see all together, like over the course of the semester, kind of exploring the timeline in that way.
So what has this been like working on this?
So fun. So fun. Our group is having so much fun.
Darwin was coming up with his theory of evolution at the time when in geology there was these tremendous advances in the field of geology, and they were understanding that the Earth was not 6,000 years old. The number they had at the time was that the Earth was 300 million years old. They got it short, but that is a huge shift in people's understanding. When people were now looking at fossils and starting to think about animals that look the same and had bone structures that were different sizes, they're starting to understand the time frame that evolution has to play with. So that's a huge thing when you think about what that means for us, right, humans, and our significance and our role in all of this. So the idea, starting from that personal connection of what's the oldest thing that you've ever seen, by the end of the lesson, the goal is to make them say, oh, that is nothing. That is, you think that's old, but actually you can't even depict the oldest thing that you know on this timeline. Who is the poster child of reproduction? Rabbits. Phew. I could have gone a lot of different ways. Another math lesson that we did in the Unity and Diversity in Evolution scope was the rabbit population growth problem. It's basically 2 rabbits are brought to an island that has no rabbits. Every month they produce another pair of rabbits, and every month after that, every pair produces another pair. And so given that, if none of them die at the end of a year, how many rabbits will there be? We talk about it a little bit, but it's mostly just to get guesses, to get kind of engage people's number sense. A number you think is too small, is too small. A number is too big, and then what's your best guess? These are too low, these are too high. What do you think it might be? 25,000, 8,000. Leroy? He says 2048. I'm sorry, Miriam? Miriam says 7,000. And then after that, people work on their own for some period of time. So about 10 minutes, people are working as individuals, and then they come together as groups, share what the strategies that they've been working on, and then work together to build towards the answer. And so the strategies that we're looking for and looking to draw out and talk about are drawing pictures and creating charts and kind of organizing our thinking in that way. So the mathematical concept that's at the heart of this, in addition to the problem-solving strategies of having to organize your thinking and keep track of this change, is exponential growth. That is 2 to the first, 2 to the second, 2 to the third, and so that you can estimate, you can calculate the number of rabbits there'll be over a period of time by doing 2 to the whatever month you're looking for. So that mathematical notation was not the goal of this lesson, but the understanding and the idea of exponential growth was, because that serves the science. According to this is the number of rabbits that would be produced after a year, right? This large number would start off small and then it would grow exponentially. And we wanted to get into that idea that though there's this potential for a population to grow exponentially, the reality of it is that what's actually going to happen is that it's going to level off and it's going to reach a carrying capacity. Because there's predators, there are other factors, and the one that we kind of took a look at was the idea that there's a limited number of resources. And so there's this potential for exponential growth to happen, but an environment is limited in its resources and it can't support that exponential growth. How does the graph look different? Is it just this continual growth that goes on and on forever? No. It has to level off. So Miriam says it goes up and it levels off, and she's throwing in a big word there, carrying capacity. It starts off growing, gets really big and big and big and big and big, but eventually it stops getting big. It doesn't keep going. It's not this J shape, but it actually turns into a little bit more of an S shape. Every population has the possibility of growing exponentially, but they're going to not have resources. They're not going to be able to do that because the resources aren't going to sustain them. Okay? And they're going to level out. The final big idea that comes out of this potential for exponential growth is that a lot more babies are going to be born than are going to survive. The question that we kind of drew out of this and left was, why do some live and why do some die? Are there factors, are there characteristics, are there traits that are more advantageous? And that kind of is moving us towards adaptation. We got rabbits. They have this potential, but they don't. And so some of them live and some of them die. So why do they die? Why do some survive and some die? In both of these activities, it's really important to start off with tapping into students' curiosity. The timeline asks students to make a personal connection to the passage of time, and the rabbit population problem asks students to make guesses, and then they're kind of invested in, did I get my guess? How close am I? Who was right? Did I win? The second thing that's really important to focus on and to not lose sight of is when doing the mathematics, to keep that spirit of question posing and problem posing and inquiry when dealing with the science. With mathematics, they're creating something that they can then make observation and scientific conjectures about. And the final thing that is really important is to decide from the activity what are the mathematical content goals you have and what are the science content goals you have. You're going to have to make choices. You might not get to all the math that you could or get to all the science, but to really think about the two separately so that you make sure that they're both going to be present in whatever the activity is.